This is the slide presentation for Chapter 5, Chemical Reactions. So the outline for the chapter, so we're going to have an introduction, we're going to talk about writing and balancing chemical equations, then we're going to do some classification of those chemical reactions, look at some more math called reaction stoichiometry, talk about reaction yields, which is like lab-related materials. And then we're going to do some quantitative chemical analysis, doing some dilutions and doing some other chemical analysis that we would use in the lab. So what are chemical reactions? Chemical reactions are the making and breaking of bonds. So in other words, we're going to make or break bonds, and this is going to lead to a chemical transformation. It's going to turn one substance into a set of other substances. And here are four classical examples of chemical reactions and categories. If I take A and B and I make a new bond, I form this new compound in which A and B have a bond between them. This is often called a combination reaction. I'm combining A and B. A second example is where I actually take a compound and I break a bond between two parts of that compound to make two new or more compounds. We often call this a decomposition reaction because we're decomposing our original reactant. A third category is where we break a bond and we make a bond. So in this case, I break the bond between A and B, and I create a new bond between C and A to form two new compounds. This is often called a displacement reaction. We're displacing B with C to form AC. The fourth example is actually where we break several bonds and we make several new bonds. So in this case, we're going to break the bond between A and B, create a new bond between A and D. We're going to break the bond between C and D and create a new bond between C and B. So we're breaking two bonds and we're making two bonds. This is often called an exchange reaction. We're exchanging, in this case, D for B and B for D. There is another term that is commonly used for this type of reaction, a double displacement reaction. Chemical reactions are symbolically represented using a set of symbols and formulas. We call these all together a chemical equation. And that's what we see down here. A plus B goes to AB. So the reactants are listed on the left, so those are our studying material. That's A and B are our reactants. The products are listed on the right. Those are our ending materials or products. There's typically an arrow between them that indicates the direction of the chemical reaction. We're going to see in examples in the future where we can have arrows going both directions. And often some reaction conditions are listed above or below the arrow itself, this X right here. That could be temperature, that could be solvents, that could be light, that could be a host of different things. A little more sophisticated than just these balls of A and B, which we call reactants and products. We like to represent the actual molecules with molecular formulas. So we literally write out the molecular formula for A and the molecular formula for B. In this case, this one reactant contains 25 carbons and 52 hydrogens. This reactant contains 38 oxygen molecules. Two of the products here, I have 25 carbon dioxide and 26 molecules of water. So that's our molecular formulas. In front of those molecular formulas, there are numerical coefficients that indicate how many of each compound are part of the reaction. These are mole quantities. So I have 1 mole of C25H52, which is wax. I have 38 moles of the oxygen molecule. It produces 25 moles of the carbon dioxide molecule and 26 moles of the water molecule. In addition to these, there are often suffixes behind the molecular formula in parentheses that indicate the physical state of the compound. For example, G for gas, S for solid, L for liquid, and AQ for aqueous. And aqueous here means in water. So if I look down at our combustion chemical reaction down here representing wax burning, I have wax as a solid. It reacts with oxygen, which is a gas. In the presence of heat or an ignition source, I form CO2, which is a gas, and water, which is a gas. Totally, that is a symbolic representation of a combustion reaction we call a chemical equation. Let's now look at some other chemical equations that are common in nature or common in life. Rusting is a chemical reaction. In rust, we take iron, we react it with oxygen to form iron 3 oxide. Okay. Notice in this case, I have 4 iron atoms, 3 oxygen molecules. I have no conditions written here, okay, and I form 2 moles of my iron 3 oxide. This chemical equation is balanced in respect that if I look at the individual atoms on each side of the arrow, I have 4 irons and 6 oxygen. If I look on the right-hand side of the arrow, I have 4 iron and 6 oxygen. That chemical reaction is balanced. That's an important part, that I have mole balancing of all my atoms. Another chemical reaction besides combustion of wax is actually combustion of petroleum products. In this case, we're representing octane burning in an automotive energy in the presence of oxygen to form carbon dioxide and water. Notice the chemical reaction is very similar to that of burning of wax. I start off with some hydrocarbon, a compound that contains carbon and hydrogen only. I react it with oxygen. It forms CO2 and water. And in this case, we trap the heat and pressure to actually run our internal combustion engine. In this case, I do have coefficients also. I have 2 moles of octane in the liquid form reacting with 25 moles of oxygen in the gas form to form 16 moles of CO2 in the gas form, 18 moles of water in the liquid form, and some heat. In addition to the internal combustion engine in a car, we also have chemical reactions ongoing in the battery. In this battery, it's a lead acid battery. One of my electrodes is a lead oxide. The other electrode is lead. In the presence of sulfur, I can react, going from left to right, to form lead sulfate and water. Notice in this case, above my arrow, I have something called discharge. I'm literally taking electrons out. If I were to put electrons into this process, I can push the reaction in the reverse direction, going from right to left. So this chemical reaction is actually an electron-mitigated chemical reaction. One of the most important chemical reactions in nature and in our lives is the photosynthesis chemical reaction, where I take CO2 from the air, I react it with water coming up the roots of a plant, and in the presence of sunlight, our energy source, and in the presence of a biological compound called chlorophyll, I can actually produce glucose, C6H12O6, and also 6-ox molecules of oxygen, which is the gas of life for humans, oxygen. So the photosynthesis reaction. Animals make glucose Animals typically use glucose both as a source of energy and as a source of carbon to build muscles and tissues. One chemical reaction that humans use is the fermentation chemical reaction, and it has been a reaction that has been known for thousands of years. We take glucose in the form of grains and sugars. In the presence of yeast, they undergo a chemical reaction to form ethanol and carbon dioxide, and they give off some energy. This yeast actually is a living organism which has some enzymes which are catalysts for the chemical reaction. Chemical reactions and their equations are literally the first step in doing stoichiometry in chemistry, all the chemical math. This is where we start. Let's go on to the next section of this chapter. In this section, we're going to learn the methodology for writing and balancing chemical equations. And we're going to do that for both molecular, ionic, and net ionic formats. Balancing chemical reaction equations is done by putting whole number stoichiometric coefficients in front of the chemical formulas for the different reactants and products. Here in this combustion reaction, you can see I have a 38, a 25, and a 26 out in front of these three molecules. It is implied that I have a 1 out here in front of this organic molecule with 25 carbons and 52 hydrogens. We just don't put it in there. We call these numbers in front of these molecules, again, stoichiometric coefficients. These coefficients represent the relative numbers of reactants and products, and these are typically referred to mole quantities. These coefficients can be correctly interpreted, however, as ratios of the different molecules. The coefficients are used to balance a chemical reaction. What that means is I need to have the same number of atoms on the left-hand side as on the right-hand side. So if I look at this combustion reaction, notice I have 25 carbons on the left. I better have 25 carbons on the right. I have 52 hydrogens on the left. I better have 52 hydrogens on the right. 26 times 2. Oxygen is a little more difficult because on the left-hand side I have them all in one molecule. In this case I have 76 oxygen atoms. On the right-hand side I have 50 oxygen atoms here, and I have 26 here. Together those add up to 76. So in fact, this is a balanced chemical reaction. The same number of atoms on the left as on the right-hand side of my chemical reaction. Let's go through the methodology because some chemical reactions are a little more complicated, but we're first going to look at a simpler version of a combustion reaction where I take one of the simplest organic molecules, methane, react it with oxygen to form CO2 and water. So if I look at this chemical reaction, I have methane reacting with oxygen to form CO2 and water. I've depicted that here. In this case, notice that I need 2 oxygen molecules to react with 1 methane molecule. My result is that I get 1 CO2 molecule and 2 water molecules. And that would be my coefficients, 1 to 2 to 1 to 2. But we know we have more than just 2 oxygen molecules and 1 methane molecule typically in a chemical reaction. So in my beaker, I have more oxygen and more methane. Those two will react under these conditions to form more water and more CO2. Notice here, if I add those all up together, I'm now starting with 2 methane molecules, but I need 4 oxygen molecules. And my reactants are going to be 2 CO2 now, this molecule, and this molecule, and I'm going to get 4 water molecules. Let's put some more methane and oxygen in our reaction vessel. In this case, I've added 2 more oxygens and 1 methane molecule. They also react to form water and CO2, and it looks like they're reacting in the same ratios. In fact, if I look at that, if I start with 3 methanes, I need 6 waters, and it produces 3 CO2s and 6 water molecules. Regardless of the absolute number of molecules involved, the ratio between the number of molecules are the same as that given in the chemical reaction equation. 1 methane reacts with 2 oxygens to form 1 CO2 and 2 waters. This is the law of definite proportions, and that's what leads to a balanced chemical reaction equation. Let's review that again, but without all the little extra oxygens and methane. So here's my chemical reaction. Methane plus 2 oxygen molecules leads to 1 carbon dioxide molecule and 2 water molecules. Again, this is my reactant side, and this is my product side. Let's formally add up all the atoms now to make sure all the atoms in each of the molecules is represented. Here I have in methane 1 carbon, 4 hydrogens. How many carbons do I have on the right hand side? I have 1 carbon, and 2 times 2, I have 4 hydrogens. On the left hand side, my reactants, I have 4 oxygens. If I go over to my right hand side, I have 2 oxygens in CO2, and I have 2 oxygens in these 2 water molecules, so I can add them all up, and in fact they do balance. I have the same number of atoms on the left hand side as I do on the right hand side. For more complicated balancing equations, I have a methodology that we often use for molecular chemical equations, those meaning covalent bonds. Let's now review that. Here I have a very simple chemical reaction. I have water. It's decomposing to form 2 hydrogens and 2 oxygens. One way to balance it is just by inspection, just sort of trial and error and working through it. So I have 2 hydrogens, 1 oxygen. I have 2 hydrogens on the right-hand side and 2 oxygens. That is an unbalanced chemical reaction. To achieve balancing, we need to add coefficients in front of the equation molecules as needed. So let's balance oxygen by adding a 2 out in front of the water. Because I need to have 2 oxygens on the left-hand side. So I put a 2 out there, remembering now that that gives me 4 hydrogens also. So I have 4 hydrogens, 2 oxygens on the reactant side. I have 2 hydrogens and 2 oxygens on the product side. My oxygens are balanced, but now my hydrogen's out. So now I'm going to actually balance the hydrogens by adding another coefficient out in front of the hydrogen on the product side. So I add a 2 out there, and that only affects hydrogens. So now I look at this chemical reaction. I have 4 hydrogens on the left, 2 times 2. I have 2 oxygens on the left, 2 times O. I have 2 hydrogens on the right-hand side, 2 times 2, and 2 oxygens in my oxygen molecule. This is a balanced chemical reaction equation. More complex chemical reaction equations actually require a better methodology than just trying these numbers in until it works. Let's go through that methodology now using a more complex combustion reaction. Let's use this combustion reaction where I'm actually looking at wax burning again to actually go through the methodology of balancing a complex molecular chemical reaction. I start off with my wax, which has 25 carbons and 52 hydrogens. I react it with oxygen to form CO2 and water. I look at this chemical reaction. I have 25 carbons on the reactant side. I have 1 carbon on the product side. I know it is not balanced. The methodology that we use is to balance the highest molecular weight element in the most complex molecule first. So my most complex molecule is the one with the largest number of atoms. So I'm going to actually balance carbon first. So I have 25 carbons on the left. I need to have 25 carbons on the right. And here I have 1 all by itself, so I just put a 25 out in front of there. Okay. The second step now is because all my other atoms now have been adjusted because I put this 25 out there. I need to balance the other elements in the most complex molecule. The C25H52 is still my most complex. The next element would be hydrogen. So I have 52 hydrogens on the left. I need to get 52 on the right. So I put the 26 coefficient out in front of water. Okay? And then I need to balance all the other elements in the other molecules. I need to balance oxygen in O2, in CO2, and water, because there are 3 different molecules that contain oxygen. Notice 1 here only contains oxygen, so I literally can add up the oxygens on the left and then just add the coefficient onto here over on the reactant side to make it work out. So here I have, again, 50 oxygen atoms. Here I have 26 for a total of 76. I put a 38 out in front of the oxygen. 38 times 2 is 76. And I only affect oxygen in this case, balancing the chemical equation. In addition to balancing our chemical reaction equation, we often want to indicate the actual states of the different molecules, either a gas, liquid, solid, or aqueous, and we're going to use these parenthetical abbreviations at the end. I know that my wax is a solid at room temperature, so I put an S there. Oxygen is a gas at room temperature, so I put a G. CO2 is a gas, and water is a gas. In addition, if there are any special conditions necessary, we want to add those either in writing or in symbols above the reaction arrow. For example, in this case, this delta, the Greek letter, actually indicates that it either started out by heating this chemical reaction or using an ignition source for this chemical reaction. And there are many different symbols and many different words that we use here depending on what the chemical reaction is. Let's do another example, and let's do a combustion reaction again. In this case, we're going to look at ethane burning, which is one of the chemical components of propane and natural gas. So in this case, I have a hydrocarbon, which has 2 carbons and 6 hydrogens reacting with oxygen, forming H2O and CO2. We're going to start with the most complex molecule and look at the highest molecular weight element, which is carbon. I got 2 on the left. I need to put a 2 out in front of CO2 on the right to balance carbon. Then I'm going to look at hydrogen. I have 6 over on the left. I can add a 3 out in front of there to balance the hydrogens. Now all I need to do is balance the oxygens. And in this case, it becomes a little more complicated. Okay, so I'm going to look at how many oxygens I have on the right-hand side. Let's see, I have 3 here plus 4 here. That is 7. I need to put a 7 out in front of my oxygen here. However, if I put a 7 or a 3.5 out there, it's not a whole number. So I put 7 halves there. And notice now it actually balances. However, in a separate step, we're going to sort of correct this fraction here because we don't like to see fractions. We like to see whole numbers, integers in front of our coefficient. So we're literally going to take that equation that we've balanced. We have 1 mole of ethane. We have 7/2 of a mole of oxygen. We have 3 moles of water and 2 moles of CO2. We're just going to multiply everything by 2. So I got 2 moles of ethane now reacting with 7 moles of oxygen to give me 6 moles of water and 4 moles of CO2. Now it's balanced, and I actually have whole number coefficients out in front. I have integers. We're then going to put down the physical states like we did last time. Gas for ethane, gas for oxygen, gas for water, and gas for CO2. And then any special conditions, we're going to designate those by writing either a word or a symbol above our reaction arrow. In this case, I'm going to put the delta in there again. How about balancing ionic chemical reactions? Those are different. Let's take a look at how we do those. Balancing ionic reaction equations. And let's look at the methodology. The first thing we do is write down the complete molecular equation using the correct formulas of the reactants and products. Here I have sodium phosphate, magnesium chloride, forming magnesium phosphate and sodium chloride. Notice that my atoms do not balance here. I have 3 sodiums on my left. I have 1 sodium on my right. Now I could balance this by inspection, by just trial and error, but it becomes difficult. So what we'd rather do in this case, we want to count each element in the reactants and products. So I write them down, and I write them as ions, because I know these are all aqueous ions, so it's an ionic equation, so they will dissociate in water, or they will precipitate, one of the two. So here we go. I count my reactants. I have 3 sodiums on my reactants, 1 sodium on my product. I have 1 phosphate, I have 2 phosphates. I have 1 magnesium, I have 3 magnesium. I have 2 chlorines and 1 chlorine. Those are not balanced. So we're going to start by changing these coefficients on one side or the other until they balance. The methodology that we use is to balance the ions on the left-hand side of the reaction equation first. So I have 3 sodiums, and I have 1 here. Let's leave that alone. On this side, I only had 1, so I'm going to actually add a 2 out so that they're balanced. And on this side, magnesium, I only had 1, but now I'm going to add a 3. Okay? And again, the chlorine, I have more than enough, so I'm going to leave that unbalanced for now. So then I fill in all my chemical reactions and see what I've changed, because I change things as I add a 2 out in front of this larger ionic equation because I affect the phosphates. So now let's record the effect that these coefficients had on the other ions on the left-hand side. So when I added a 2 out in front of the phosphate, I also added a 2 out in front of the sodium. So now I have 6 sodiums. When I added a 3 out in front of the magnesium chloride, I actually now have 6 chlorines there too. 3 times 6. So I changed all those. Notice now I'm balanced in the center, but not balanced here. Now I'm going to look to the product side to fix those values because I have sodiums and chlorines that are alone here. So when I do that, I just add a 6 out in front of the sodium, and I add a 6 out in front of the chlorine, and that's shown here in blue. And then I add all those up. All of my atoms are now balanced, which means all of the atoms in my molecules are balanced. Okay, so I have 2 sodiums here times 3. It gives me 6. I have 6 sodiums on the right-hand side. I have 2 phosphates. Here I have 2 phosphates on the product side. I have 3 magnesiums on the reactant side. I have 3 magnesiums on the product. I have 6 chlorines and 6 chlorines. I have a balanced chemical reaction. Many of the compounds have a suffix AQ on them. That means they dissociate into ions in water. And in fact, we can use that to actually simplify our chemical reaction. This would represent the full molecular reaction, but we could simplify this as an ionic chemical reaction. Let's look at the different levels that we use to represent aqueous ionic chemical reactions. Whenever ions are involved, the chemical equations can be written at different levels of detail. For example, I have my chemical formula here in this chemical reaction. I have calcium chloride reacting with silver nitrate to form calcium nitrate and silver chloride. Notice this is not balanced. I go through the methodology of balancing it all, and I find out that I need 2 of these silver nitrate molecules, and I need 2 of the silver chloride molecules. Now this is balanced. Okay. When I put this materials into water, they tend to dissociate in water to form distinct ions. So I can sort of separate them out. My calcium chloride in water forms calcium and chloride. Okay. My silver forms silver and nitrate ions. My calcium nitrate forms calcium and nitrate ions. Notice that I didn't have in here silver chloride. That's because there's an S here. That's actually a solid that precipitates out a solution, so it does not form ions. So you can see why these parenthetical suffixes are so important when I'm writing an ionic equation, because this does not ionize in water. It remains as a compound and it precipitates out. It does not dissolve in water. The fourth type of ionic equation is actually a complete ionic equation, where I take all my individual ions on the left-hand side and I add them all up into one big equation. So you can see here I have calcium, chlorine, silver, nitrate, my reaction arrow, calcium, nitrate, and silver chloride, my solid. If I look closely, there are several species that are present on both sides of the arrow. I have one calcium on the left, I have a calcium on the right. So did calcium go to make calcium? Sure, it forms ions. I also have the nitrate on both sides. I have NO3 here and NO3 here. I have 2 of them. They're both aqueous. We call these actually spectator ions because they do not react in this chemical reaction. They just dissociate into ions. So they largely just remain their charge neutrality, and they neither form physical nor process changes, so no chemical reaction. So what I can do is I can take my complete ionic formula now and sort of eliminate the calciums from both sides, eliminate the nitrates from both sides, and then rewrite my chemical reaction equation as a net ionic equation. That is where I take the 2 ions on the left, they react to form my compound on the right, my solid compound that is not soluble in water, that is not ionic in water. Let's do a second example and determine all the different levels of ionic equations. The first thing I'm going to do for this reaction is write out the chemical formulas in an unbalanced. So I have sodium sulfate reacting with barium hydroxide to form sodium hydroxide and barium sulfate. I go then through the ionic methodology to balance that chemical reaction. It turns out that I just need to add a 2 coefficient in front of the sodium hydroxide, and it is balanced. And then I need, for the next level, I'm going to actually write out the ionic components. So I know sodium sulfate is aqueous. I know that barium hydroxide is aqueous. I know that sodium hydroxide is aqueous. So those 3 compounds will dissociate into their ions in water. Barium sulfate is a solid, and it will not, as stated down here on the bottom. So let's write out the ionic equations for each of those components. Sodium sulfate dissociates into sodium and sulfate. Barium hydroxide dissociates into barium and hydroxide. Sodium hydroxide into sodium and hydroxide. Notice I sort of kept and added a coefficient in front of some of these to make sure that I have it balanced also, because I need two sodiums here because I started off two sodiums there. Also notice I sort of keep the charges involved in these ones too. So I need to include the charge and the states. In this case, they're all aqueous. Let's now go ahead into a complete ionic equation. So I have sodium, sulfate, barium, hydroxide, forming sodium, hydroxide, and barium sulfate. I'm now going to form the Net Ionic Equation by eliminating all my spectator ions. I look on both sides. I notice I have sodiums on both sides. Cross those off. I notice I have hydroxides on both sides. Cross those off. And by doing that, I come up with the Net Ionic Equation. It's those species that actually react to form a new compound. Barium reacts with sulfate to form barium sulfate. The sodium and hydroxide are just in there as spectators. In this section, we're going to look at how chemists actually classify chemical reactions. So we'll look at some different ways that we classify them. But then we're going to look at some specific ones. We're going to look at some acid-base reactions. We're going to look at some solubility rules which help us classify them. And then finally, we're going to look at calculating some oxidation states. The first reaction we're going to take a look at is called a synthesis reaction. Earlier we called it a combination reaction. The same thing, just different chemists using different terms. We're taking X and Y and we're going to make a bond between them. We're going to combine them to form the compound X and Y. Several examples of that would be like magnesium burning in the presence of oxygen to form magnesium oxide. It's a combination reaction. We're synthesizing something. Another example would be taking this element sulfur, reacting it with the molecule oxygen to make sulfur dioxide. And this is an example of it in the side of a volcano. Sulfur burning at high temperatures, combining two components together and synthesizing a new product. The second classification which we're going to talk about are decomposition reactions, where we take a compound that has a bond between two molecules and we literally break bonds to form, in this case, X and Z. An example of that would be calcium carbonate reacting at very high temperatures to form calcium oxide and CO2 gas. Burning calcium carbonate. Another example of that would be taking this nitrate compound, which is also called nitroglycerin, actually exposing it to a shock, and it decomposes to form 12 carbon dioxide molecules, 10 water molecules, 6 nitrogen molecules, and an oxygen molecule. Obviously, we know that when this material decomposes, it actually releases a lot of energy. And that is typical of a lot of decomposition reactions. Breaking bonds, releasing energy. The third category is single displacement reactions, where I'm going to take one of these molecules and I'm going to displace it with another molecule or atom. In this case, A is going to displace the red ball here. Some examples of that are the thermite process, which takes aluminum and iron 3 oxide, reacts that together to form metallic iron and aluminum oxide. Notice in this case we actually have iron here, which is metallic. We use that all the time for welding. So we use this chemical process when we're actually welding railroad ties together because we can do a chemical reaction. A couple other examples, taking zinc solid, which is metallic, reacting it with silver nitrate. We replace the silver with the zinc to form silver nitrate and silver. Okay. Another reaction is where halides undergo displacement reactions in addition to the two examples of metals that we just showed. Here I have fluorine reacting with lithium chloride. The fluorine actually displaces the lithium here to form lithium fluoride and chlorine gas in this reaction. Again, all these chemical reactions are balanced. And finally, our fourth type of chemical reaction classification, a double displacement reaction, often called an exchange reaction or a metathesis reaction. Here I do two displacements. In this case, I take the yellow ball and I remove the green and I replace it with the blue, and also on this side I replace the blue on this side with the green. So I'm displacing both of them. Some examples of that are actually precipitation reactions, which we've discussed a little bit, where in this case, I take a compound called silver nitrate, I react it with sodium chloride, I displace the nitrate on this molecule with the chlorine, and I displace the chlorine on this molecule with the nitrate to form silver chloride, which is a solid so it precipitates, and aqueous sodium nitrate. Another example of that would be this reaction of lead nitrate reacting with potassium dichromate. Again, both of them are aqueous, and I do a double displacement to displace one of the sides of the ionic compound with another. In this case, I replace the nitrate with the chromate to form lead chromate, and I replace the chromate with the nitrate to form potassium nitrate in this case. Again, one of these compounds is insoluble, so it's a solid. These two are classified as precipitation reactions. Chemists have some other groups or categories that they use to classify chemical reactions. We just looked at these four on top. Our book tends to group them into classes of three, and so our discussion will concentrate on precipitation reactions, acid-base reactions, which are both double displacement reactions, and then we're going to talk about oxidation reduction reactions, which are sort of a combination of single replacement reactions, synthesis, and decomposition. So oxidation reduction reactions include a large number of the four categories which we already discussed. So let's start off and let's start looking at precipitation reactions. Let's first take a closer look at precipitation reactions. These are reactions which initially start with the reactants are dissolved substances and then they react to form one or more solid products. We often refer to these as either double replacement or double displacement or even metathesis reactions, depending on what part of the world you're from and which textbook you're reading. Many of these reactions actually involve the exchange of ions between ionic compounds, and that's what we're going to look at in this example. Please note that these types of reactions are very common in nature and also in industry. We use them all the time to make different types of compounds. Let's first look at the reaction of sodium chloride, which is an aqueous solution, meaning it's dissolved in water and it's ionic, reacting with silver nitrate, also dissolved in water and ionic, to form sodium nitrate, which is in water and ionic, and silver chloride, which is actually a solid. If we were to write the Net Ionic Equation, get rid of all those compounds, those elements that are just spectator ions. The sodiums aren't involved in the chemical reaction. Get rid of those. The nitrate molecules are not involved with those, so get rid of those. We end up with the Net Ionic Equation where silver reacts with chlorine to form silver chloride, the solid. Notice I've drawn a little arrow down here. Often chemists will add that. It indicates that it is physically a precipitate in this chemical reaction. I take silver nitrate with sodium chloride, pour them together, I form this white precipitate, a precipitation reaction. Which product precipitates depends on the solubility. In this case, silver chloride is insoluble, but let's look at some rules for insolubility and solubility. Okay. So solubility is the maximum concentration of a substance that can be achieved under specified conditions like heat and stirring and pressure, things like that. Substances that have a large solubility, a lot of it dissolves in solution, are said to be soluble. Substances that have relatively low solubilities, those that do not dissolve very well, are called insoluble. Having said that, typically there's always a little bit of an insoluble compound that's soluble, and there's always a little bit of a soluble compound that's insoluble. It's sort of a relative thing. Relatively large, relatively low. When we think of solubility, we think of a solvent. So the solvent in this case, as we're looking at down here, is all these water molecules, the red and white ones. This compound, sodium chloride, is crystalline, but when I dump it into water, some of the negative charges on water attract the positive charges of the sodium. Some of the positive charges on water attract the negative charges on the chlorine, and they sort of break this ionic bonds and they get dissolved, they get dispersed within the water. This does indicate that I need a lot more water than I have sodium chloride, because eventually if I don't have enough water, some of this will stay in the crystalline form and will be insoluble. Let's look at two tables of solubility: compounds that are soluble, compounds that are insoluble. And these tables are not perfect. There are some exceptions. So if I look at the soluble compounds, these are ionic compounds now. I look at lithium, sodium, potassium, Rb, cesium. Those are typically all soluble, and they all come from group 1 metal cations. Those are in the very first column going down the periodic table. In addition, ammonia, my halides, my acetates, my bicarbonates, the nitrates, the chlorates, and the sulfate ions, those all tend to be soluble ions. There are some exceptions, however. If I have a halide of both silver, mercury, or lead, those tend to be insoluble. So if I have silver forming an ionic compound, they're going to be insoluble. In addition, if I have sulfates of silver, barium, calcium, mercury, lead, and strontium, those also tend to be insoluble. So we have just soluble cations and we have insoluble, depending on what their ionic structure is. We can now look at insoluble ions, and generally we think of carbonates, chromates, phosphates, sulfides, and hydroxides as being insoluble compounds if they're part of the ionic compound. However, there's also some exceptions here. So carbonates are insoluble unless they're paired up with a group 1 metal cation, then they tend to be soluble. If I look at phosphates, and any of these here, if they react with ammonia and they pair up, they tend to be soluble. And also, any of my hydroxides, if they pair up to form an ionic compound with the group 1 metals and barium, they tend to be soluble. So these tables are sort of useful, however there are some exceptions to them, but they show the general trends. So a substance will precipitate when conditions are just such that its concentration exceeds its solubility. It's no longer soluble. It can no longer be surrounded by the solvent and dispersed. Let's look at some examples of solids that are soluble in water. For example, if I take this compound with 2 ammonia molecules and 1 sulfur atom here, it's a solid. In water, it dissociates into its ions, and both of the ions are soluble in water, so I don't see any precipitate if I mix those together. They literally dissolve. If I take silver nitrate, which is a solid, and put it in water, it too becomes the nitrate anion and the silver cation. They're both soluble in water. So again, I do not see any precipitate when I dissolve sodium nitrate in water. If I take copper 2 nitrate and dissolve it in water, I get 2 ions again that are soluble in water, and in my solution I do not see any precipitate. If I add a lot of these materials, eventually I will see material that doesn't dissolve, but it doesn't precipitate out of solution. It just doesn't dissolve. Let's now look at some insoluble ions. If I take sodium sulfide and react it with cadmium nitrate, I get sodium nitrate and cadmium sulfide. In this case, one of my compounds is actually a solid. And if I look closely at this chemical reaction, it's actually a double displacement reaction or a precipitation reaction. So in this case, my cadmium sulfide is actually an insoluble solid. I can also look at this reaction where I have SbCl3 reacting with H2S to form HCl and my SbS3. In this case, this last compound at the end here tends to be a solid, so it precipitates out of reaction to form this orange-yellow solid. And finally, if I take sodium sulfide, react it with lead nitrate, I get sodium nitrate and lead sulfide. This lead sulfide here is an insoluble solid. I see this black precipitate that forms. We can simplify all of these precipitation reactions by using the Net Ionic Equation, because obviously in all three of these chemical reactions there's these bystander ions that are not part of the reaction to form my precipitate. So let's look at one. If I take potassium iodide, react it with lead nitrate, I get lead iodide and potassium nitrate. Again, my Net Ionic Equation, I'm literally going to eliminate the potassiums and the nitrate because they actually, if I drew out the ionic equations, they're just spectator ions. And so I end up with lead reacting with iodine to form lead iodide. And that lead iodide is a yellow precipitate. Another example would be my sodium sulfate reacting with barium hydroxide to form sodium hydroxide and barium sulfate. I write the Net Ionic Equation, getting rid of all the spectator ions, the sodiums and the hydroxide. I end up with barium reacting with sulfate to form barium sulfate, which is a white solid. It's a precipitate. Let's now look at some special aqueous reactions, ones that happen in water. We often call these acid-base reactions, and that's our next category of chemical reaction. Let's now look at a special case of chemical reactions that occur in water, acid-base reactions. An acid-base reaction is one in which a hydrogen ion, H+, is transferred from one chemical species to another. In the example shown here, HCl contains hydrogen, water. If my hydrogen is transferred to my water, I end up with a chloride anion and a hydronium cation. H3O+ is often referred to again as a hydronium cation. An aqueous acid is a substance that will dissolve in water like HCl, and it tends to transfer a hydrogen over to water. Virtually every HCl molecule that I dissolve in water undergoes this reaction, so we sort of classify HCl as a strong acid, meaning the arrow in here is a big arrow going to the right. So all of my molecules end up being chloride anions and hydronium ions. Some other examples of strong acids are hydrobromic acid, hydrochloric acid, which is in the example above, hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Notice the common feature of all of these species is that they have a hydrogen here. And when you put them in water, they tend to lose the hydrogen and it forms hydronium ions. Sulfuric acid actually has 2 hydrogens on it, so it is actually a biacid, and both of those hydrogens can be transferred over to water to form hydronium ions. We use strong acids all the time in chemistry. However, there are a lot more weak acids, and those are ones that only partially react with water. Only some of the hydrogens come off of it. So an example of that would be acetic acid, where if I put that in water, it has a hydrogen on it. It can react with water. In this case, I have the symbol L here indicating that that's my solvent. It's a liquid. That hydrogen comes off to form the acetate anion and the hydronium cation. However, most of the molecules in solution exist as acetic acid. Only a number of them exist as the carbonate anion. That's why I have drawn an arrow here going back toward reactants here. This is what we call an equilibrium reaction. So that double arrow indicates that it's a partial reaction, and that eventually they'll form an equilibrium where there'll be so many of these in solution and there'll be so many of these in solution. In the case of acetic acid, only about 1% of the acetic acid molecules exist in the ionized form or the acetate form. And we see examples of acetic acid being used all the time, both in the chemistry laboratory and a lot when we're cooking. It's considered vinegar, apple cider vinegar, even some of our wines are vinegar wines, and when we pickle things, we tend to use vinegar because it sort of stabilizes the chemical structure and makes them so that they last a long time in the cupboard. Acetic acid. Another example of a weak acid in nature is citric acid. And if you've taken biology, you might know this in the citric acid cycle, sometimes called the tricarboxylic acid cycle today, or even the Krebs cycle. It's where I take citric acid and I make the anion. It's a weak acid. Some other examples of weak acid are formic acid. We've already talked about acetic, oxalic acid, benzoic acid, ascorbic acid, and citric acid. And we see all of these acids used all the time in foods, and biologically we use these acids to maintain a healthy body. For example, ascorbic acid is vitamin C. It's actually a chemical compound that's necessary for many of the enzymes to work in our bodies. An aqueous base is a substance that will react with water to yield hydroxide ions, OH-. For example, when we take sodium hydroxide as a solid and we add water to it, it is soluble in the fact that it forms sodium ions and hydroxide ions. The most common bases are ionic compounds that are composed of our alkali and our alkali earth metal cations, meaning my groups 1 and groups 2, so sodium, potassium, calcium, barium, things like that. A base that completely dissociates in water, has an arrow strongly going to the right-hand side, is considered a strong base. The process of dissociation is a physical process. It's not an acid-base reaction. So I'm not reacting an acid with a base. I'm just putting the base in water and it's dissociating into ions. So this is the Net Ionic Equation. I'm not reacting with water here. So I have sodium as aqueous and I have hydroxide in aqueous and water. Some other examples of strong bases besides sodium hydroxide are potassium hydroxide, barium hydroxide, and calcium hydroxide. Sodium and potassium hydroxide are often used in the kitchen here because they're such strong bases. They tend to be very reactive, and they can actually react with burnt-on organic compounds either in our oven or that are clogged down in our drain. They'll actually dissolve things like hair and burnt-on pizza crust from the oven. Just like acids, there are examples of weak bases. When I think of a weak base, I always draw the chemical reaction equation with this equilibrium 2 arrows here. A lot of our weak bases have nitrogen on them. So if I take ammonia, aqueous here meaning it's in water, react it with water, it forms ammonia cations and hydroxide anions. In this case, that is actually a chemical reaction, right? Because I'm actually removing one of the hydrogens here. I mean, my base is plucking one of those hydrogens off to actually form hydroxide anions here. So this is considered an acid-base reaction. Some common examples of weak bases are ammonia, methylamine, and pyridine. The common thing here that you notice is that they all contain nitrogen. And we know that nitrogen has a lone pair of electrons, and that can be reactive. It can react with one of the hydrogens on water to pull it off to form the ammonium cation. We also see examples of this in household life. Windex contains ammonia, and also glass cleaner and bench cleaner. We use that for cleaning because, again, it's very reactive, but it's not like it's going to dissolve my countertops or dissolve my windows because it's weak. So what happens when I mix an acid with a base? What happens is I get a neutralization reaction. I literally have an acid reacting with a base, often to form a salt and water. Because I know acids react to form H+, bases dissolve to form OH-, they can react together to form water, and their counterpart ions can react to form the salt. Let's look at a few examples. Let's first start off and look at magnesium hydroxide. That would be a base. It's got hydroxide ions that can dissociate. HCl, I know that's a strong acid. When they react, I have that magnesium reacts with the chlorine to actually form magnesium chloride, and I form water. Notice this is still just the molecular equation. I want to actually get down to the net ionic equation so I can look to make sure what ions are actually spectator ions. So I first again write out my complete ionic equation, and then I start getting rid of my spectator ions. So in this case, I see a chlorine on the left-hand side, I see a chlorine on the right-hand side. Those are my only two spectator ions, so I end up with my molecular equation, magnesium hydroxide reacting with my hydrogen cation, forming magnesium cation and water. Let's look at a few other neutralization reactions. Here I take hydrochloric acid reacting with sodium hydroxide to form sodium chloride, which is a salt, but it's a soluble salt, and water, which here I have as a liquid because it's also my solvent. I work my way down here getting rid of all the spectator ions, chlorine, sodium, sodium, chlorine. I end up with my net ionic equation, which is my hydrogen anion and my hydroxide anion, and those reactions go to form water. If I look at another chemical reaction of a strong acid and a strong base, this case I take hydrobromic acid reacting with potassium hydroxide to form potassium chloride, which is also an aqueous compound, so it dissolves and forms ions and reacts to form water. I draw my complete ionic equation. I get rid of my spectator ions, bromine, potassium, potassium bromine, I end up with, again, H plus OH minus gives me water. Notice in this case, my net ionic equation for both of these chemical reactions is identical. That's because I'm reacting a strong acid with a strong base in both cases. In this case, the chemical reaction is just H plus and OH minus forming water. Now let's look at our third and final classification of chemical reactions, oxidation reduction reactions, often called redox reactions. We name this redox just because they involve reduction and oxidation. So oxidation is classified as the loss of electrons. Reduction is actually the gain of electrons. And we often have this little mnemonic that we use to actually remember this, oil rig. Oxidation is loss of electrons, and reduction is gain. Oil rig. I use that all the time. So let's look at this chemical reaction here where I take 2 sodium atoms, react them with 1 chlorine molecule to form 2 sodium chloride molecules. In this case, solid. So I have a solid reacting with a gas to form a solid. Whenever we have oxidation reactions, it's actually helpful to split the overall reaction into what we call half reactions, okay? I first look at the sodium. I take 2 sodium atoms and then I ionize them. I actually form the sodium cations, and I need to make sure that my reaction is balanced, so I lose 2 electrons here. Notice I have 2 pluses and 2 minuses. Those react and are neutral, so I have a neutral on the left. I have neutral on the right. Let's do the same thing for chlorine. I have neutral chlorine on the left. I add 2 electrons to that. I form 2 chloride atoms now. So I have anions here. So in this case, my chlorine has gained electrons. Let's see, that means it must have been reduced because it gained an electron. My sodium has lost electrons, so I go up here. That must be an oxidation reaction, so my sodium is oxidized. So sodium in this case acts as a reducing agent. It's sort of redundant. It actually provides the electrons or reduces chlorine. So the sodium reduces chlorine, and the chlorine oxidizes sodium. And we get these words in here, we use them all the time. Sodium is a reducing agent because it actually gets oxidized. And chlorine is an oxidizing agent because it gets reduced. The words reductant and oxidant are also used in these cases. A lot of words to remember. When we talk about chemical reactions between covalently bound reactants that form covalently bound products, we're not actually transferring electrons between species. We're forming covalent bonds, covalent compounds, so we're sharing electrons. But we still consider these oxidation reduction reactions in the sense that electrons are still being moved around. We use the concept of oxidation number, or sometimes called oxidation state. That's where an element in a compound is sort of given the charge its atoms would possess if the compound were ionic. That's sort of a little confusing, but let's look at some of the rules and some examples to see how that works. So here are some rules for assigning oxidation numbers. It's that fake charge that they would have if they were ionic. The oxidation number for an atom in its elemental state or substance is 0. For example, all my noble gases like helium, neon, and xenon all have an oxidation state of 0. Any metal that is metallic in its native state, it doesn't have a charge on it, it's not ionic, it has an oxidation number of 0. The oxidation number for a monatomic ion is equal to the ion's charge. For example, Mg plus, I give it a +1. Cl minus, I give it a -1. Br minus, I give it a -1 also, etc. all the way down the periodic table. There's another rule that we use, and this is very important, especially when we talk about organic compounds. If hydrogen is combined with a nonmetal, for example with carbon, we give it a +1 oxidation state. When it's combined with a metal, we give it a -1. Oxygen, we just about nearly always give it a -2. Okay, so that's whether it's attached to a metal or to an organic compound like carbon. Sometimes, there's a few exceptions, we have peroxides which are ions of oxygen itself. We give that a -1. And very rarely we have a -1 for oxygen. We call it superoxides, and we give that a -1. Positive values are also used when they combine with fluoride, and it may vary. Okay, so there are some exceptions. In general, for organic compounds, we give oxygen a -2, and we give hydrogen a +1, and that is for a large number of chemical reactions. Halogens is -1 for fluorine always, and -1 for all the other halogens like chlorine, bromine, and iodine. Except when it's combined with oxygen or other halogens. Positive oxidation numbers are given in these cases, and these are exceptions. The fourth rule is that the sum of all the oxidation numbers for all the atoms in a molecule or in a polyatomic ion equals the charge on that molecule or ion. Let's see what that means. Okay. Let's look at an example. H2S. So that's a covalent molecule. I know that one of my rules is that I give H a +1 for a majority of things. How about sulfur? Well, actually, I don't know what that is. We need to calculate that. But I know that rule 4, it tells me that the net charge of my oxidation numbers must equal the charge on my neutral molecule, and that's 0. So my charge on H2S is 0. I know that every hydrogen I'm going to give a +1 oxidation state, so I can sort of use the math here to figure that one out. So I have 2 times 1 plus 1 times X. I'm going to solve for the oxidation number on sulfur. That works out that X must equal 2. So sulfur in this molecule has an oxidation number or oxidation state of -2. Let's do the same now for SO3 2-. This whole molecule is a polyatomic ion. It is bound together by covalent bonds. The oxidation number for oxygen is -2, so I can use that in my formula. So my charge total on SO3 - 2 is 2. I know that I have 3 oxygens. Each of them is going to have a -2 oxidation state. I can then solve for the oxidation state on sulfur because I know my charge of the polyatomic ion is -2. Solve for all that. In this case, sulfur has an oxidation state of +4. Oxidation numbers. Let's look at assigning oxidation numbers to a compound that is a combination of a sodium ion and a sulfate polyatomic ion. In order to assign oxidation numbers, it's actually convenient in ionic compounds to actually assign the oxidation numbers for the cation and anion separately. So sodium, when I put that on water, it dissociates into sodium cations, so I can easily assign its oxidation number. It's just the charge on the sodium cation, +1. For the polyatomic sulfate, I then have to use my guidelines. So for example, let's assume that the oxygens on my sulfate are all -2 per guideline number 3. The oxidation for sulfur then can be calculated based on the assumption that the sulfate has a -2 charge, therefore we're going to call the overall oxidation state as -2 for the whole polyatomic ion. For oxygen, we're going to assume that its oxidation state is -2, so 4 times -2. Now all I have to do is solve for S, so 1 sulfur times its oxidation number, doing the mathematics. In this case, it turns out that the oxidation number for sulfur in this molecule is +6 in this case. So that's its oxidation number. So let's look back at oxidation reduction reactions. So in this case, where we're not explicitly exchanging a charge in some cases, oxidation is actually the increase in oxidation number. So when I oxidize something, I increase the oxidation number. Oil rig, oxidation is loss. So I've gone from a negative to a more positive number. Reduction is the decrease in oxidation number, so I'm going toward a more negative number. I'm going toward more electrons. Oil rig, reduction is gain. And that's the end of this section. Let's now look specifically at some oxidation reduction reactions, and let's actually go through the methodology of actually balancing one of these oxidation reduction reactions. Two examples of oxidation reduction reactions are combustion reactions. In this case, it's slightly different than burning an organic material with carbon. I'm actually combust aluminum with ammonium chlorate to form aluminum oxide, aluminum chloride, water, and N2 gas. Notice when I look at this chemical reaction, the oxidation state of aluminum, because it's in its pure form here on the reactant side, is actually 0. So it has an oxidation number of 0. If I look at the oxidation number on the product side, it's going to be +3. And so this molecule, let's see, it has lost electrons because it's becoming more positive. Oil rig, oxidation is lost. So this has been oxidized. Aluminum has been oxidized. If I went through the methodology here, there's something else in this equation that would have been reduced. Let's next look at a single displacement reaction. In this case, it is also an oxidation reduction reaction because I am actually changing the oxidation state of some of the components. In this reaction, I'm reacting copper with silver nitrate to form copper nitrate and silver metal. So copper starts out with its oxidation state of 0. Silver, because it's aqueous ionic, actually starts out at +2. And then copper ends up at +2, so it got oxidized. And silver ends up at 0, so it gained electron number, so it got reduced. So oxidation reactions. Let's now look at balancing redox reactions, and let's specifically look at a redox reaction that takes place in water. Because this is often the case, my reaction actually involves the water, either the hydronium ions or the hydroxide ions. They're either reactants or products, so we're going to include them in the chemical reaction, in the balancing of the chemical reaction. Although these species are not actually oxidized or reduced, they do participate in the chemical reaction in other ways. These reactions are extremely difficult to balance by just inspection, looking at and putting numbers in front. So the methodology that chemists actually use is actually what we call half reaction method, where we actually take the main molecular reaction and we break it down into half reactions, going from this ionic equation to this balanced ionic equation. Okay? Because notice up here on the top, I do not have any oxygens on the right-hand side, but I need to put oxygens there, and water is a good source for them. But if I put water in there, I also need to put H plus in there on the other side too, so it's sort of a balancing act. Let's now work our way through that methodology of balancing redox reactions. Here's just a list, and we're going to walk through each of these individually. There are 9 steps in actually balancing a redox reaction. And I'm going to read through those, and then we'll use an example where we look at each of these steps individually. We need to write the 2 individual half reactions, what's being oxidized and what's being reduced. And then we need to balance the elements in those half reactions with oxygen and hydrogen. We're going to use oxygen from water to actually balance the oxygen, and then we're going to use hydrogen, adding H plus ions to balance the hydrogens. We're then going to balance the charges, because I know these are ionic reactions. There's actually going to be ions being moved back and forth, so we can use electrons to balance those. If necessary, we're going to multiply each half reaction with a coefficient so that we get an integral number in front of each of the electrons too. So we'll look through an example of that. We're then going to add the balanced half reactions together and simplify the whole reaction by removing species that are sort of spectator species from both sides again. It's a little bit different in step 8 here. If we're doing a reaction that involves hydroxide, we're just going to use hydroxide to balance one of the sides instead of H plus. Once we're all done, number 9 down here is actually to see that the number of atoms and the total charges are all balanced on both sides of the chemical reaction, on the reactant side and on the product side. So here's the example we're going to look at. We're going to look at this chromium 2 oxygen 7 anion reacting with iron to form chromium 3 and iron. Let's now write the half reactions. So I'm going to say, well, what got oxidized and what got reduced? My iron went from a +2 to a +3, so it got oxidized. It lost electrons. My chromium here, it actually changed. It had to have been reduced because it went up to +3. Okay, so it's the reduction part of the system. So I just write those down. I put down that iron gets oxidized from iron +2 to iron +3. My chromate gets reduced from chromium 2 oxygen -2 to chromium 3+. Those are my 2 half reactions. Notice that the atoms are not balanced down here and the charges are not balanced. I need to go to. In step 2, we want to balance all the elements except oxygen and hydrogen. So I look at the oxidation half reaction for iron, and I notice that it's already balanced. I have 1 iron atom going to 1 iron atom. Next, I look at the reduction half reaction for chromium, and on the left-hand side, I have 2 chromiums. On the right-hand side, I only have 1, so I'm just going to add the coefficient 2 out in front of the chromium 3+ side to balance it. So now all of my heavy atoms are balanced. I just need to worry about hydrogen and oxygen. So the first thing I'm going to do is I'm going to balance the oxygen by adding water to any of the sides. In the iron half reaction, the oxidation side, there are no oxygens. I don't have to do anything. On the chromium half reaction, I need to have oxygens on the right-hand side. I notice on the reactant side, I have 7 oxygens. I need to have 7 oxygens on the product side. So I just add 7 water molecules. Now my oxygens aren't balanced. However, now I've sort of messed up my hydrogens because I have 14 on the right-hand side. I have 0 on the left-hand side. We're going to balance those atoms by adding H plus to the sides, the reactants and products. Again, the iron half reaction does not contain hydrogen. It's fine the way it is. My chromium half reaction shows that I have 14 atoms on the right and none on the reactant left-hand side. So I'm just going to add 14 H pluses in there to make it all balance out. So my atoms now are starting to look like they're adding up together. In step 5, we're going to balance the charges. So I first look at the iron half reaction. I notice there's a +2 on the left and a +3 on the right. I've actually oxidized the iron. So I need to actually add an electron to one side or the other. Which side to add it to? Because electrons are negative, I want to add it to the product side because I have 3 pluses plus 1 negatives. That equals 2 pluses. Now they're all balanced. So you got to make sure you add the electron to the correct side. Also in step 5, I'm going to balance the charges on the chromium half reaction. So if I look at this, I look at the total charges on each side. So on the reactant side, I have 1 times -2. I have 1 minus 2 here. I have 14 plus 1. So adding that all together, I have plus 12 on the left-hand side. If I look at the right-hand side, the products, I have 2 times +3, so that's +6. So on the right-hand side, I have +6. So I need to make those equal. So I need to add 6 more electrons onto the left-hand side to sort of equal everything out here. Because I have +12 on the left, +6 on the right. I'm going to make this side +6 also by adding more negatives to the left-hand side. Now the charges are all balanced. So my half reactions are both balanced relative to atoms and to charges. I just need to add those both up now. So everything on the left-hand side of my half reaction gets added to the left-hand side of my other half reaction. Everything on the right-hand side of my first half reaction gets added onto the right-hand side of my second half reaction. Putting those all together, I get a total half reaction. So I get 6 irons, 1 chromate, 14 hydrogen, 6 electrons. I get my 6 iron atoms plus 3 charge, my 6 electrons, my chromium ion, and my water, adding that all up. Okay. Only the 6 electrons are redundant species. Okay, so I need to cross off any redundant species that are on either side, and I can see I just need to cross off the electrons here. Okay, so if I cross off the electrons, my reaction simplifies to the following reaction. And number 9, I skipped number 8 because I'm not working in base. I'm just going to confirm that all my elements on the left-hand side, my reactants, equal to the amount of elements on my right-hand side, and add those all up. On the reactant side, I have 6 irons. On the product side, I have 6 irons. On the reactant side, I have 2 chromiums, and on the right-hand side, I have 2 chromiums. 7 oxygens on the left, 7 oxygens on the right. 14 hydrogens on the left, 14 hydrogens on the left. My charges all balance out now. So I have 6 times 2. I have -2. Add that all up. I get a +24 on the left, and I add all these up. I get a +24 on the right. This is a balanced ionic oxidation reduction reaction. Now that we have sort of a basic understanding of balancing chemical equations, Let's see how that plays into actually doing some more stoichiometry. In other words, using those chemical equations to solve mathematical equations in chemistry. The concept of mass, moles, and solution molarity will be discussed in more detail. Balanced chemical reactions are actually used in the laboratory all the time to determine a number of important values. For one, the amount of one reactant required to react with a given amount of another reactant. That is the stoichiometric amounts. You can see here in this equation, I need 1 molecule of nitrogen to react with 3 molecules of hydrogen. It also tells us the amount of reactant needed to yield a given amount of product. In other words, I need 1 of these and 3 of these to give me 2 of these. These are all stoichiometric amounts and stoichiometric factors. From this chemical equation, I know that the number of nitrogen molecules that need to react to form a ammonia molecule is in a 1:2 ratio in molecules. 1 of these molecules will give me 2 of those molecules. It also shows me the number of hydrogen molecules necessary to react to form ammonia molecules. In this case, it's 3 hydrogen molecules to give me 2 ammonia molecules. So I'm reacting in a 3:2 ratio. I can actually put these into what we call factors, just putting them into literally as a fraction here. And I can do that either as molecules as or moles. So let's take a look at that. I note in order to form 2 molecules of ammonia, I need 1 molecule of nitrogen. That also is true for moles, because I know moles is just a number of particles. I need 2 moles of ammonia for every 1 mole of nitrogen. I can do the same for hydrogen. For every 3 hydrogen molecules that I have, I can produce 2 ammonia molecules, or for every 3 moles of hydrogen that I have, I'm going to produce 2 moles of hydrogen. Now that we have these fractional factors, I can use those to do more math. Let's look at an example. Here in example 1, the question is, how many moles of iodine are required to react with 0.429 moles of aluminum in the laboratory? The first thing we need is actually a balanced chemical equation so we know what we're going to actually produce. So I know how much aluminum I have. I want to know how much iodine I need to produce aluminum iodide. In this chemical reaction, I need 2 moles of aluminum to react with 3 moles of iodine to produce 2 moles of aluminum iodide. I can use those stoichiometric coefficients to actually create stoichiometric factors. So I know that for every 2 moles of aluminum, I need 3 moles of iodine, or vice versa. For every 3 moles of iodine, I need 2 moles of aluminum. And how much aluminum iodine am I going to produce? It depends on how much of aluminum and iodine I have. But I know for every 2 moles of aluminum, I will produce 2 moles of aluminum iodide. For every 3 moles of iodine, I will produce 2 moles of aluminum iodide. In order to solve our example up here, I just need to pick the right stoichiometric factor. I know I'm starting with 0.429 moles of aluminum, so I put that in the far left of the equation. Then I pick the right stoichiometric factor to convert moles of aluminum to moles of iodine. Notice when I set up this equation here, I can cancel moles of aluminum in my numerator with my moles of aluminum in the denominator, do the mathematics. What this tells me is that I need 0.644 moles of iodine to react with all of the aluminum in my laboratory experiment. Here's a second example. The question is, I'm in the laboratory. what mass of sodium hydroxide, NaOH, so that's what I'm looking for, a mass now, would be required to produce 16 grams of the antacid milk of magnesia, magnesium hydroxide. And I need to do that. First thing I need to do is actually write a balanced chemical equation. I have magnesium chloride reacting with sodium hydroxide to form magnesium hydroxide and sodium chloride. I want to know how much of this would be required to actually make 16 grams of this material. The first thing I do, because I'm looking for sodium hydroxide and magnesium, I pick out the stoichiometric coefficients. For every 2 moles of sodium hydroxide, I'm going to produce 1 mole of magnesium hydroxide. So let's just set that up. I have 16 grams of antacid. Put that out in front here. That's my magnesium hydroxide. I know that I need to convert that to moles first because it's in grams. My stoichiometric factor is in moles. So I can convert from grams to moles just by using the molecular weight of magnesium hydroxide, which is 58.3 grams of magnesium hydroxide for every mole of magnesium hydroxide. So now my grams of magnesium hydroxide in the numerator cancels my grams of magnesium hydroxide in the denominator. I'm left with moles of magnesium hydroxide. I have a nice convenient way now to convert that into moles of sodium hydroxide just using my stoichiometric factor that I took off of the balanced chemical equation. So now my moles of magnesium hydroxide cancels my moles of magnesium hydroxide. I'm left with moles of sodium hydroxide. But the question wants to know what mass of sodium hydroxide I need. I can just convert that to mass using its molecular weight, because I know 1 mole of sodium hydroxide actually reacts, it has a molecular weight of 40 grams. So if I look at all that and I start canceling out, I cancel that with that, I cancel that with that, I cancel that units with those units. I'm left with grams of sodium hydroxide. Do all the mathematics. It turns out I need 22 grams of sodium hydroxide to fully react with my and produce my 18 grams of my magnesium hydroxide. I am back in the lab, and I want to know what mass of sucrose, C12, H22, O11 would be required to fully react with 25.0 grams of potassium chlorate. The first thing I need is a balanced chemical equation, so I set that up. I see after doing the stoichiometry, I see that I have 8 moles of potassium chlorate reacts with 1 mole of sucrose to produce 8 moles of potassium chloride, 12 moles of CO2, and 11 moles of water. I now need to pick out the right stoichiometric factor to do my conversion up here. I need to relate sucrose to grams of potassium chlorate, and that happens to be 1 mole of sucrose is equivalent to 8 moles of potassium chlorate in the reaction. So I'm going to start off by putting my known quantity on the left-hand side of my mathematical equation to do the algebra. I need to convert now my grams of potassium chloride into moles of potassium chloride. So I use the molecular weight of potassium chlorate. I look that up in a table, or I go to the periodic table and add together the molecular weights of potassium, chlorine, and oxygen. I can now cancel out the grams of potassium chlorate. I now have moles of potassium chlorate. I know the relationship in my chemical reaction between moles of potassium chlorate and moles of sucrose. I set up that stoichiometric factor in my algebraic equation. I can now cancel out my moles of potassium chlorate. I now have converted my grams of potassium chloride into moles of sucrose needed. I can then convert moles of sucrose into grams of sucrose because I work with grams in the lab, typically not with moles. So I go to the periodic table, I look up the molecular weights for carbon, hydrogen, and oxygen, add those all up together to give me the molecular weight of sucrose. I know there are 342.0 grams of sucrose in 1 mole of sucrose. I set up that factor so that my moles of sucrose in the numerator cancel the moles of sucrose in the denominator. Do all the mathematics on my calculator and come up, I need 8.72 grams of sucrose to react with my 25.0 grams of my potassium chlorate. I'm back in the lab for a 4th time. In this case, I have 25.0 grams of chlorine gas and it's expensive. And I want to know how much sodium hydroxide I need to actually react with that very expensive chlorine gas. So I'm going to use a chemical equation to that and some stoichiometric factors. I set up my balanced chemical equation for the reaction. 2 moles of sodium hydroxide reacts with 1 mole of chlorine gas to give me 1 mole of sodium hypochlorite, 1 mole of sodium chloride, and 1 mole of water. I then find the stoichiometric factor that relates my chlorine gas to my sodium hydroxide. Those are the 2 things I'm looking for here. And so I find that for every 2 moles of sodium hydroxide, I need 1 mole of chlorine gas, or vice versa. If I have 1 mole of chlorine gas, I need 2 moles of sodium hydroxide. I set up my algebraic equation again. In this case, I have 25 grams of chlorine gas. I need to convert that to moles of gas, so I use its molecular weight. My grams of chlorine cancel. I now have moles of chlorine. I use my stoichiometric factor from my balanced chemical equation. My moles of chlorine cancel. I then have moles of sodium hydroxide. I need to have grams of sodium hydroxide. I look for the molecular weight of sodium hydroxide, set up that in my algebraic question, and I'm left with grams of sodium hydroxide. I need to have 28.2 grams of sodium hydroxide to react fully with 25 grams of chlorine. However, because my sodium chloride is so expensive, and sometimes I make mistakes in the lab or I don't get 100% yields, I'm actually going to use a little bit more than that stoichiometric amount of lab because it's cheap. Sodium hydroxide is very cheap. So I'm going to use 30 grams. Having said that, it still will only react with literally my moles of sodium hydroxide here. It'll just be some extra sodium hydroxide at the end. Often, when I go into the laboratory, I do not get 100% yield. And so we have something called reaction yields. And in order to understand reaction yields, I need to talk about theoretical yields, and I need to talk about limiting reactants or reagents. And then finally, when I get down to finishing up all the arithmetic and algebra, I'm going to find out and calculate the percent yield for a chemical reaction. So I go into the chemistry lab. Let's say I have 2 reagents that I'm going to react together in a reaction vessel. I want to calculate how much product I actually produce. That is called yield. Let's consider the following reaction. If I have methane gas reacting with oxygen gas, forming CO2 and water. That's a combustion reaction, right? Okay. So it depends on how much of these materials I have. I know from the balanced chemical reaction, for every mole of methane gas that I have, I need 2 moles of oxygen gas. But what if I don't have these stoichiometric amounts? What if I have instead only 1 mole of methane gas and I do not have 2 moles of oxygen? I need to determine which of these two is my limiting reagent. Okay? So let's take a look at how we can do that. So in this chemical reaction as it stands right here, for every 1 mole of methane gas I have, I need 2 moles of oxygen to give me 1 mole of CO2 and 1 mole of water. In other words, I don't have any excess. If they reacted 100% with each other, both of them would be limiting because I have the right stoichiometric amounts. I have 1 mole of methane and 1 mole of oxygen. Let's instead look at the fact where I have 1 mole of methane and I have 5 moles of oxygen. So I have extra oxygen. In this case, I can still only produce 1 mole of CO2 and 1 mole of water because I have a limiting reagent. My reaction is limited by the stoichiometric ratios of 1 to 2. So I look at this, I have XX oxygen, and my limiting reagent right now would be my methane gas. Let's look now where I have 2 moles of methane, and I'm going to react that with 2 moles of oxygen. From the chemical reaction, I know I can still only produce 1 mole of CO2 and 2 moles of water in this case. That's because in this case, my oxygen is actually my limiting reagent. I have excess methane. I only need 1 mole to react with 2 moles, but I have 2 moles. Let's look at something that's a little more difficult here, not quite as obvious. I have 1.5 moles of methane reacting with 3.2 moles of oxygen. I do a little bit of mathematics and I find out that, oh, in this case, that is still in a 1 to 2 ratio. So I have 1 mole of CO2 or 1.5 moles of CO2. That's going to make 3 moles of water. And so in this case, they're both limiting in this case. I don't have any excess. I can use either amount to calculate how much of my product I get. That might have been a fast explanation. So let's actually look at sort of an example and some methodology for calculating this a little bit easier. Let's look at that same reaction. How much water and CO2 will be produced if I start with 25 grams of methane and 90 grams of oxygen? I need to find out which of these two is actually my limiting reagent. In order to do that, I need to calculate how many moles of each of these I have, because moles actually tells me how many molecules of each I have, and I know they react based on the balanced chemical equation by molecules or by moles. So the first thing I do is write the balanced chemical equation. I then go ahead and determine the moles of each of those. So the first thing I do is I calculate how many moles of methane I have. I have 1.56 moles. I calculate how many moles of oxygen I have. I take 90 grams of oxygen times its molecular weight to give me 2.85 moles of oxygen. Notice in this case, I have some, not easily recognizable numbers. So I know that for every mole of methane I have, I need 2 moles of oxygen. That's my stoichiometric factor right from the chemical reaction. So let's see at how many moles of oxygen I'll need. If I start with 1.56 moles of methane, and I know they react in a ratio of 2 moles of oxygen reacts with 1 mole of methane, my moles of methane cancel. I'm left with how many moles of oxygen I need to react with all my methane, and that's 3.12 moles. So how do I relate that back? I need 3.12 2 moles, but I only have 2.82. I calculated that up here. So I do not have enough oxygen to react with all my methane. In other words, oxygen is my limiting reagent. That tells me how much CO2 and water I can produce. This is the only molar amount I can use to do that. So I'm going to use oxygen moles now to calculate my yields. I can now calculate the amount of products that are formed by using that amount of my limiting reagent. Again, we'll do this using my stoichiometric coefficients from my balanced chemical equation. I know we've just calculated that my oxygen is my limiting reagent, so I need to start with that. Okay, so I'm going to take my grams of oxygen, convert it to moles of oxygen, convert my moles of oxygen to moles of water, and I know from my chemical reaction, for every 2 moles of oxygen, I will produce 2 moles of water. So I've set up the stoichiometric factor so that my moles of oxygen cancel. And then I want to convert my moles of water into grams of water. I use its molecular weight. And for every 90 grams of oxygen, I can theoretically produce 50.6 grams of water if I didn't spill any. If the chemical reaction went to 100% completion. I can also calculate how much CO2 is produced by starting again with my 90 grams of oxygen, my limiting reagent, convert it to moles of oxygen, convert it to moles of CO2 this time using a different stoichiometric factor. I know that I produce only 1 mole of CO2 for every mole of oxygen I start with. I then want to convert moles of CO2 into grams of CO2 using its molecular weight. And finally, it turns out that theoretically I can form 61.88 grams of CO2. Again, these are theoretical amounts because there's lots of opportunities in the laboratory to actually lose yield. So ideally, my theoretical yield would be 50.6 grams of water or 61.88 grams of CO2. When I do the chemical reaction in the lab, I can actually weigh these two and find an actual yield and compare it to my theoretical yields. So actual yields are different. They're laboratory measurements. Theoretical yields are based on what I've started with and how much I could theoretically produce if everything went 100% good. So I've gone into the laboratory and I've done the chemical reaction, reacting oxygen with methane to form CO2 and water, and I've actually analyzed my products and weighed them. That would be my actual yield. And then when I finally do the algebra, it turns out that my actual yield was actually less than my theoretical yield, and that is very common. This is often due to things like spills or competing side reactions. Remember the law of multiple proportions? My chemical reagents could have reacted in a different way, or they might not have gone to completion. I didn't leave them react long enough. I didn't put enough energy in. I didn't stir them. Or the products could actually be difficult to recover. I might not be able to recover all the products. And I've got the etc. down here. There are lots of reasons that I do not isolate all my product. To the extent to which a reaction's theoretical is achieved is commonly called its percent yield. It's comparing my theoretical yield to my actual yield. So percent yield is equal to the actual yield that I measure in the laboratory divided by the theoretical yield that I calculate, and that's usually calculated based on one of the two starting reagents. It's usually calculated based on my limiting reagent. So when calculating percent yields, both yields must be expressed in the same units so that the units will all cancel. So we need to make sure we get grams and kilograms and So let's calculate the percent yields for both the products for the following reaction. Again, I take methane plus oxygen to give me CO2 and water. If I have 25 grams of methane is mixed with 90 grams of oxygen, I know that my 90 grams of oxygen is my limiting reagent. I've calculated my theoretical yields already of 61.88 grams of CO2 and 50.6 grams of water. In the laboratory, I'm able to isolate and measure only 52.88 grams of CO2. It's a gas and hard to measure the weight. And I've isolated 40.1 grams of water in the laboratory. Let's calculate percent yields for both. I know the theoretical yields of both. I know the actual yields of both. I can now do my percent yield calculation. So I take 52.88 grams of CO2, my actual yield, divided by my 61.88 grams of CO2 theoretical yield times 100%, I get an 85.5% yield of CO2. Ideally, that would be 100%, but in most cases, it's never 100%. I can do the same thing for my yield of water. I take my actual yield of 40.1 grams of water divided by my theoretical yield of 50.6 grams of water times 100%. I get 79.2% yield of water. Notice they are not the same. It depends on my methodology for weighing a gas versus the methodology of water, or what sort of side reactions went on. Let's do another example. I want to know the percent yield when I react 1.274 grams of copper sulfate with some zinc, and I'm going to use extra zinc metal. I don't exactly know how much it is, but I know it's way in excess because it's cheap. And then finally, I know that when I isolate my final product, which is the copper metal, I actually measure it at 0.392 grams of copper are isolated. So I always need to write a balanced chemical reaction so I know the stoichiometric coefficients of my chemical reaction. I have 1 mole of copper sulfate reacts with 1 mole of zinc metal to form 1 mole of copper metal and 1 mole of zinc sulfate. I have excess zinc sulfate, so my limiting reagent is therefore the copper sulfate, and I know how much that is. So I can set up the stoichiometric equation here, my algebraic equation. I'm starting with 1.274 grams of copper sulfate. I'm going to convert that over to moles of copper sulfate using its molecular weight. I'm then going to use my stoichiometric factor based on the balanced chemical reaction to convert moles of copper sulfate into my moles of product copper. Convert my moles of copper back into grams of copper now. Theoretically, I should be able to get 0.5072 grams of copper. I know that in the laboratory I isolated 0.392, so I can now calculate my percent yield, taking my actual yield, dividing by my theoretical yield, times 100% to give me 77.7% copper metal isolated. Let's do another practical example. What is the percent yield of the reaction where I have 65.0 grams of lithium oxide reacting with 80.0 grams of water? I write down my balanced chemical reaction. I got my lithium oxide reacting with water to form 2 moles of lithium hydroxide. In the laboratory, I actually measured how much lithium oxide I produced, and it was 85.5. So I'm going to use all these numbers to actually calculate my percent yield. The first thing we need to do is calculate our limiting reagent. So I calculate how many moles of lithium oxide I start with and how many moles of water I start with. I know they react in a 1-to-1 ratio. I have 2.17 moles of lithium oxide reacting with 4.44 moles of water. Water is very cheap, so I just added excess. I have literally more moles of water than I need. So for every mole of lithium oxide, I need 1 mole of water from the equation. So I do not have enough lithium oxide to react with all the water. So my lithium oxide is my limiting reagent. We're going to use that for doing all our calculations now. So in the third step, I'm going to calculate my theoretical yield, starting with the mass of my limiting reagent, 65.0 grams of lithium oxide. Convert it to moles of lithium oxide using the molecular weight. Convert it to moles of lithium hydroxide, my product, because I'm using my stoichiometric factor here again. For every mole of lithium oxide I start with, I'm going to produce 2 moles of lithium hydroxide. I have moles of lithium hydroxide. I'm going to convert that to grams of hydroxide using my molecular weight relationship. I get 104 grams of lithium hydroxide as my theoretical yield. I can then just now go back in and plug that into my percent yield calculation. So I have my actual yield, which is 85.5 grams of lithium oxide. I've calculated my theoretical yield of 104 grams of lithium hydroxide times 100%. That gives me 82.2 grams of lithium hydroxide. My percent yield calculated. In addition to just weighing out our reagents and then weighing our products to actually determine percent yield, there are several other techniques used in the laboratory where our stoichiometric coefficients from our balanced chemical reaction equations are very useful. Those include titrations and gravimetric analysis. And that's what we're going to talk about next. We call these two types of analysis quantitative analysis because they actually determine an amount. So we get a number. Okay. One of them is titration, one of them is gravimetric analysis. Let me walk you through the steps here. So here I have a Erlenmeyer flask in which I put in some solution. In this case, let's call it an acid solution. And I have a known amount of it, but I don't know how many molecules of acid I have. I then have to add what is called an indicator to my Erlenmeyer flask. It's just something that changes color based on acid-base properties or quantitative reactions. I then, above my Erlenmeyer, I put a graduated burette, which I read an initial reading. This orange chemical in this burette reacts with whatever the blue chemical is in my Erlenmeyer flask. I start to release my material and I keep on adding it until I see this color change. The color change is due to the indicator, which tells me that I have actually reacted this orange material with my blue material 100% in stoichiometric amounts. So I've done a 100% chemical reaction. So many molecules of the orange stuff reacts with the stoichiometric amount of the blue stuff. And then I can just read my readings between my initial reading on my burette and the final reading on the burette. And I know how much material I have added. I know the concentrations of the material, so I can calculate how much reagent of the blue material was actually part of the blue material, because it's probably made up of both water and some chemical compound. Gravimetric is another technique which is used to determine the amount of one component in a reaction. Here I have a beaker which contains this pink compound. I actually put it on the balance and weigh it. So it contains the compound and some water. I then add some other compound that forms a precipitation reaction in stoichiometric amounts, and I add excess of this material in this eyedropper here so that all of my material reacts that can, and I actually form this yellow solid, which I then filter through a piece of filter paper, and then I dry it and I weigh the orange stuff. I know stoichiometrically how these two chemicals react, how the yellow stuff is formed from the reaction of the material in my eyedropper and in my beaker, so I can use the balanced chemical equation to determine how much of this pink reagent I actually started with. Let's walk through that again. So I'm starting off with two solutions. One is called the Analyte. That's the solution containing a reactant of unknown amount or unknown concentration. In this case, that's the blue stuff in my Erlenmeyer flask. I also have something called a titrant, which is a solution of known concentration of one reactant. And I know how these react because I'm going to look at the balanced chemical reaction equation. By measuring the amount of one titrant solution required to completely react with the analyte, an equivalence point can be determined. That's where my indicator changes color, for example. Then I can do a bunch of calculations to determine what the concentration of my analyte was that I started with. So what exactly is that indicator? It's actually added to the analyte to impart a color change when I've added enough of my analyte to actually react it. And so there has to be a very crisp color change. And once I see that color change, I need to stop adding any of my analyte. So the volume of titrant actually measured is called the endpoint, how much of this orange stuff I add. The difference between the equivalence point and the endpoint should be negligible. So when I hit an endpoint, it must also equal my equivalence point. I don't keep on adding. Let's look at a real-world application of titration. If I start off with a 50 milliliter sample of hydrochloric acid and I do not know the concentration, that's what I want to find out. And I do a titration where I see the endpoint after I've added 35.23 milliliters of a 0.250 molar solution of the titrant. Again, I want to calculate the concentration of HCl. I need to have a balanced stoichiometric reaction equation for this reaction. I'm reacting hydrochloric acid with sodium hydroxide to form sodium chloride and water. And I also need to have an indicator that tells me once I've got equal molar amounts of these two reagents. So here's the methodology. I know the volume of sodium hydroxide that I add as a titrant to reach my endpoint. I take that molar amount, convert it to the right units. In this case, I'm converting it to liters because I want to have everything in moles per liters or more molarity. I need to convert that to the number of moles now, so I take 0.250 moles per liter of sodium hydroxide. I now know the number of moles of sodium hydroxide. I can use my stoichiometric factor to actually calculate how many moles of HCl I have reacted with, because I know 1 mole of sodium hydroxide reacts with 1 mole of HCl. I know I've hit the endpoint because I have a color change. I now just calculate the number of moles of HCl that I have in my 50 milliliters. From that value, I can also now calculate a concentration, molarity. Because I know molarity is equal to moles of HCl, I know that. In liters of solution, I know that it's 50. Do the math, making sure I get all the units right. I have a concentration of HCl of 0.176 molar concentration using titration to determine that. This is a more detailed outline of gravimetric analysis. So in this analysis, the mass is measured of my initial sample, and it could be liquid, so I know its mass. I then do a chemical reaction where I add a chemical that causes a physical change in state of the analyte, for example, precipitation. And then the solid precipitate is separated from the other components, which might be water, the liquid, through a process called filtration. And then I just need to measure the mass of that isolated precipitate, that isolated solid. From the stoichiometric reaction equation, I can actually then use calculations to determine the amount of that component that was isolated and then back calculate its concentration in the initial amount of solution. Let's look at an example of how we use gravimetric analysis to determine the composition of a mixture. I have a solid mixture that weighs 0.4550 grams, and it contains some magnesium sulfate along with some other stuff, and I don't know what that other stuff is. I dissolve it in water, and then I treat it with something, and I treat it with something in excess. That's something that reacts with the magnesium sulfate specifically to form a product that precipitates. So if I take magnesium sulfate, I can actually react it with barium nitrate in a 1:1 molar ratio to form barium sulfate, which is a precipitate, so it's a solid, so I can weigh that once I do the reaction, and it forms magnesium nitrate. And none of the other components of my mixture do this reaction. So I'm going to start off with my known quantity that I've isolated of the barium sulfate, doing my gravimetric analysis. I've weighed it. I ended up with 0.6168 grams of barium sulfate. I need to convert that to moles because we always talk about the number of atoms, the number of molecules, the number of moles that are reacting in a reaction. So I convert that using the molecular weight into moles of barium sulfate. I know from my balanced chemical reaction equation that 1 mole of magnesium sulfate reacts with barium nitrate to form 1 mole of barium sulfate. So 1 mole of magnesium sulfate results in 1 mole of barium sulfate. I use that stoichiometric factor to convert my moles of barium sulfate into moles of magnesium sulfate, my starting material that I want to know. I then convert my moles of magnesium sulfate into grams of magnesium sulfate using the molecular weight. And if I look at that, I end up with 0.3181 grams of magnesium sulfate. That's how much magnesium sulfate was actually in my starting mixture. I can then just do a simple ratio to calculate the concentration. So I take the mass of magnesium sulfate that I calculated based on my gravimetric analysis, divided by the mass of the initial sample, which was a mixture, times 100%. Do the simple division here. It turns out I have 69.91% of my mixture is magnesium sulfate, all determined by gravimetric analysis. Let's look at another example. Polyethylene is a hydrocarbon polymer used to make food storage bags and many other flexible plastic items, toys, car seats, etc. I do a combustion analysis, so I burn the polyethylene. So a combustion analysis of a 0.00126 gram sample of polyethylene yields 0.00394 grams of CO2 and 0.00161 grams of water. I want to know what the empirical formula is of the polyethylene. So I write a balanced chemical equation. In this case, it's going to be for every mole of polyethylene I have. I'm going to add excess oxygen. I'm going to form X moles of CO2 and Y over 2 moles of water. The first thing I do is I want to calculate the number of moles of CO2 and H2O that I produce because I measured those in the lab. And again, I want to work with numbers that relate moles to moles. So I calculate the number of moles of CO2 that I isolated using the molecular weight of CO2, using my conversion factor to generate how many moles of carbon I actually have in there. So I know for every mole of CO2 that I produce 1 mole of carbon. That's from this value right here. And I end up with 8.95 times 10 to the minus 5 moles of carbon. I now want to calculate the amount of hydrogen in polyethylene. Again, our goal is to find out what these coefficients are, what X is, how many carbons I have, and how many hydrogens I have in a molar ratios. So I then take my grams of hydrogen that was isolated, convert it to moles, and I know that for every mole of water that I have, I'm going to have 2 moles of hydrogen. So I do that calculation again. So in this reaction, I have 1.79 times 10 to the minus 4 moles of hydrogen. I set those up in my stoichiometric ratios, moles of hydrogen to moles of carbon, because that's what I want to figure out, right? I want to figure out how many moles of each of these I have so I can calculate my coefficients here. I set those up and I have for every 2 moles of hydrogen, I have 1 mole of carbon. That's my empirical formula for polyethylene. So in this case, I don't know the exact formula because polyethylene is actually a big polymer. So this could be 1 million and this could be 2 million, or this could be 5 and this could be 10. It's just a ratio here. So all I'm calculating is the empirical formula in this case. And that's the end of Chapter 5, looking at chemical reactions. We're now going to look at states of matter, solids, liquids, and gases.